My name is Matheus Simões, and I'm going to present Guilhèm's work. So the topic of this presentation is improving single trace attacks on NTT for Cortex M4. So as you maybe know, side channel attack is a technique to retrieve sensitive information from cryptography devices. And there are basically two classes of side channel attacks. The first one is vertical attack, in which you're going to do the acquisition of thousands and millions of power traces and try to correlate the information for those traces with the secrets you want to find. The second class are horizontal attack, in which you try to retrieve the secret using a single execution of your algorithm. So this presentation focused on this single trace attack, and I'm going to show you the context with some key elements to implement this attack. Then I will try to show you how to implement it with some results, and then we conclude with some perspectives on his work. So the core idea behind this attack is belief propagation. It's a technique in which I'm going to describe my algorithm using factographs. And in this factograph, variable nodes, as you can see, they define unknown quantities in my implementation, in my executor. So this I'm trying to find, actually to attack those in unknown quantities. Then I can model the relation between those variables using factor nodes, those green squares on the image. And since it's a graph, undirected graph, I can pass messages between the nodes, and those messages, they mean actually they are the belief, they denote that as belief, and actually they define the probability distribution among those variables that I want to compute. So in this kind of attack, I can model my algorithm using belief propagation model, factographs, and I will iterate the attack by doing the acquisition of setting the inputs, and then I'm going to pass messages on the factograph until the output, and then I do this kind of ping pong, traveling back to the output to the inputs of my graph. So this is one iteration of this kind of attack. And I'm going to apply that on Kyber, on the NTT function on Kyber. So NTT is important because you use it to ease the multiplication of polynomials in Kyber. And there it's composed of 7 butterfly layers and 256 coefficients. So what I'm trying to do here to find is how can I find those coefficients here in this implementation. And we are going to attack the last implementation version of this of Kyber for Cortex M4, in which I have a 32-bit word containing 2 coefficients. In that way, I can implement 2 butterfly operations at once. So to give you some information on the leakage model used in this work, so we based the leakage model on the Hamming weights. Since I have a 32-bit word, I have from 0 to 32 values for Hamming weights. And I assume that I have leakages when data are written on registers or run, and I can measure that. On top of that measurement, I will add some Gaussian noise that I can configure actually the standard deviation, denoted as sigma m. So when I produce the traces, let's say because everything is simulated here, as I'm going to explain, I can configure, I can set this the noise I want. So how can I implement this attack in practice? So here in the image, you can see one layer of entity you can see two butterfly operations, so 4 coefficients here. And I have 4 types of factor nodes here in this case. The first factor node, denoted L, so the pink blocks, they define the leakages when I do load or store operations. So since I have 32 registers and each coefficient, they are 16 bits, this factor node trying to model the load or store operations, they are linked to 2 variables. The second node I have, it's the I, the green one. And in this factor node, I try to model the leakage from operations on a single coefficient, and the V node for a pair of coefficients. Finally, I have this fourth factor node, trying to model the relation between the 2 coefficients. It is actually the butterfly operation. So I have those factor nodes here, and I can model the leakage to each one depending on the behavior of my function. They also applied 2 techniques to optimize the attack. The first one is message damping. So when I have one iteration, I'm trying to compute actually the probability distribution on the variables on the computation. But it's possible that I start to oscillate between 2 possible values, and I keep oscillating on that, and never converge to something, to a final probability. So to avoid that, they added some weights to the message passing, taking it into account the last message that was sent. And with that, they can try to unbalance this message oscillation, trying to break and converge to some value. The second technique they used is message pruning, and in this case, it's simply to ignore low probabilities outcomes to speed up the attack. So for the setup of this attack, so everything is simulated. They used Python 3 for simulation with just-in-time compilation with Number. And also they use 32 cores to speed up everything again. And how do they did the acquisition of traces, power traces? So again, they sample a random input for the coefficients, for the 256 coefficients, and they did one computation of the NTT, so one iteration, this ping-pong manner. And they measured the Hamming weights of all the variables written in registers with this sigma m noise they added on after the measurements. So they measure the Hamming weights with this noise. And to attack that, so they have access to this noised values they acquired. And they can do now to try to model using factor graphs based on those measurements. And they do, now actually they do this. They use the factor nodes to do this ping pong actually iteration, trying to find the highest probability outcomes, trying to do these iterations on the NTT graphs modeled with factor graphs. And there are three possible cases here in this case. The first one, it can converge to something, so the highest probability and the attack has succeeded. The second case is that we achieve an iteration limit, 100 iterations to be more exact. And failure is when you can't obtain a conclusion about this attack. Like say, you have a 0 probability outcome for every case. So some results about this attack. So in the first case, I know the noise used, so I can just set up my attack to use the same standard deviation sigma for the added noise. And as you can see, up to sigma 4, all the attacks have succeeded. So all cases, you have 100% of perfect success. Up to sigma 5, they achieved 75% of success rate. And in all cases, actually for sigma 4, the computation can be done in less than 3 hours. But in reality, we don't know the noise used. So in this case, they fixed sigma m to 4, and then they can vary the sigma f, so it's the noise from the factographs. And as you can see, they achieve a high success rate yet. So it shows that even if this imperfect setup, let's say for configuring the noise, you can achieve a very high success rate. This image also tells us that if you don't know the noise, which is the real case, it's better to overestimate the noise than underestimate it, because you have a better results when you even with overestimation of the noise. And again, we can the computation is done with less than 3 hours. So how can I exploit this attack to obtain to retrieve sensitive information? The first case, I can use it in the encryption phase of Kyber to retrieve the plain text, or I can use it on the key generation. And in this case, since I'm attacking the NTT function, I can use it to retrieve S and E to obtain the keys. So it depends on the application and what you want to retrieve, but you have those cases that can be exploited using this technique. And how can I mitigate this attack? So yesterday I was trying to defend masking, showing that it's a very nice countermeasure against side channel attacks, and actually it is, but in the case of vertical attacks, let's say. But here it's a horizontal attack, and I can iterate more, trying to attack share by share, and at the end, recombine the shares and retrieve the secret. So masking actually is going to reduce the noise tolerance of my attack. So masking is not an effective side channel countermeasure here in this case. What can I do is shuffling. So to randomize the execution of the NETT computation, trying to decorrelate the timing of the evaluation with the corresponding data. So I have still 1 more minute to conclude. So Guilhèm's work, they adapt the belief propagation technique to attack the optimized version of Cortex-M for implementation of Kyber. They showed that with accurate modeling, so if they know the noise used, they achieve a very high rates for this attack, up to standard deviation 5, sigma 5. However, if you don't know the noise, if it's the real case, you can still achieve a good success rate using this technique. So, some references. Thank you for your attention. I hope it was clear, and I'm ready to answer some questions.
Any question? Please come to the microphone if you have any question. He generously accepted to take these questions, although it is not an option.
I would try, but I highly recommend to contact Guilhèm if you want more precise information on.
Thank you for the presentation. Aydın Aysu from North Carolina State University. Yeah. So my question is about the uniqueness or the novelty of this work. So as you mentioned here, there have been many previous attacks, single trace attacks on NTT and other functions from my group, from this group and other groups. So what is the the value proposition here?
That the value proposition, I believe that there's a new version of the Cortex M4 implementation of Kyber.
Okay.
So one of the main contributions here is to use belief propagation, to adapt belief propagation attack on this implementation.
Okay, so
it was optimized for Cortex M4.
Okay, then a follow-up question would be, what changes between unoptimized versus optimized implementation of Kyber that disables previous attacks but is enabled with this attack?
No, I'm sorry, I don't know how to defend this now.
I can follow up with the authors, yeah.
Yeah.
But so essentially the goal is to extend previous attacks to a slightly changed implementation.
Exactly. To show a new use case, let's say, how to implement this and it still works, let's say.
Sounds
good. Yeah.
Okay, thank you.
Any other questions? So let's thank the speaker again.
Thank you.
Our second presentation, titled as Detour Layout-Aware Reroute Attack Vulnerability Assessment and Analysis. Our presenter is Minyan Gao. And Minyan received a BS degree from Northwest University, Xi'an, China in 2016, and the ME degree in electrical engineering from University of Virginia. She is currently working toward a PhD degree in electrical engineering at Florida Institute for National Security, University of Florida. Her current research interests include hardware security and trust, VLSI CAD, VLSI physical design. Yes, please. The floor is yours.
Hello, everyone. I'm Minyan from University of Florida, and my presentation today is focusing on our work, Detour, against the Reroute probing attacks. So we are hearing and using these amazing technologies every day, like the IoT and autonomous, which need the support of the secure cyberspace, where the hardware security is the bedrock. We have been seeing quite a few attack vectors in the entire chip's life cycle, like the Trojan insertion and the IP piracy at the pre-silicon stage, and like the fault injection and the side channel vulnerabilities to be exploited at the post-silicon stage. Among them, microprobing attack is one of the most powerful attacks, since it can directly access the internal assets within the IC. As we can see in the left figure here, probing attacks can create a conducting path between the target assets and the chip surface to enable, which can, such that the sensitive information in the IC can be measured using the external needles. A typical microprobing attack relies on the capabilities of the advanced focused ion beam equipment to create a very tiny mining hole, as shown in the middle diagram. The hole will penetrate through covering wires at higher metal layers to reach the target wire underneath. Obviously, a small mining hole is very advantageous to adversaries, since negligible footprints would be observed. To enable a high precision probing attack, the fib with the higher aspect ratio is more desirable because it determines the sharpness of the mining hole. And microprobing attacks are very well known for confidentiality compromise, whereas it can also be effective for the integrity violations by injecting faults, because Philippe can not only do the mining but also do the deposition. So there are a few real-world microprobing attack cases to give us a more intuitive understanding. Probing can enable the encrypted memory readout, and it can also steal the information through the machine code of programs, and it can also do the invasive memory fault injection. So the mainstream attack model for the FIB is the bypass attack, where adversaries utilize the space between covering wires at higher metal layers and search for a good chance to access the target wires below without cutting cutting off any other nets, especially the shield nets. The right figure is the trim view and the bird view of the intrusion. This attack is very easy to implement, but we can see that its main downside is that it passively searches for the exploitable space instead of creating attack surfaces by itself. And for the bypass attack, we already have a few publications on how to do the assess and quantify the vulnerabilities at the high layout level. An important metric is the exposed area, that is the area that can be exploited in a FIB probing attack to have the access to the target assets. However, as mentioned, FIB can not only do the mining but also do the deposition, which implies FIB can edit circuits at nanoscale precision. This inspires a new attack model, Reroute attack, which is far more dangerous and potent than the bypass attack. So the figures here contrast the conventional bypass attack and the emerging reroute attack. The main difference is that covering or shield wires are edited by FIB or not, so the probing path can bypass them without impacting the original functionality. The edit trace is essentially a copy path between two equipotential points, making a probing and the reroute attack makes the attackers very easy to access the underneath sensitive signals. So although this emerging reroute attack is very powerful, unfortunately, very few research has been done on reroute attack. And this paper presents a very few specific reroute examples, because in their paper they assume that the shield wires on the top metal layers would be a fixed structure. Like here are some examples. For example, they assume that the shield wires can be formed like a snake-like wires or the parallel wires, and to probe a probing area of a fixed size. How many traces that need to be added here, and how many vias that needed to be here, and the sum of the total length. Therefore, we might need a comprehensive and a layout solution for threat evaluation at the pre-silicon stage. To summarize the motivations, users and designers caring about the reroute attack will be curious how they can know how vulnerable their physical design is against the reroute attacks. With that, we present our Detour framework here to address it by incorporating the dedicated metrics that can quantify the design vulnerabilities. And our approach is a linear programming based that can evaluate the reroute attack efforts. We also added the visualization results that will help us gain more understanding about what we have done. And our tool is a fully automated and it can be seamlessly integrated into the existing EDA development flow. And the experiments results show that we can achieve the optimal shield configuration at the SOC level. So here is our Detour framework. Basically, the input will be the design layout that you want to do the analysis on, and the target and the list of the target nets and the fit parameters, and which is the aspect ratio. And second, so our main framework consists of the three parts. First is the probing area calculation, which is to identify all target nets carrying security assets in the specified layout. And next is the shield nets extraction, which is to extract the location of all the shield nets given the identified target nets. And last part is the reroute attack efforts estimation, which will quantify the attack efforts considering both the shield and the target nets. And for the output, it will include all the number of vias and traces to be added, and the layout where added traces length. And so our main goal is to minimize the probing area and the number of traces to be added and the total length. So our problem will be given the probing area and the shield wires in this area. We want to do the quantify of the sum of the reroute attack efforts. And the constraints to be added here they are all technology dependent. And for example, the distance between the vias to be added to the nets, and distance between the vias to vias, and so on and so forth. So here, so in more detail, as we have discussed before, the inputs will be the design layout and the technology-dependent library constraints, and the list of the target or the shield nets and the probing area. So first we would do the initialization, which would be to load the design layout and initialize the target function. And second, we would do the edit trace formulation and add the constraints. And then we would do the linear programming to do the calculation and give us the outputs. So in order to perform the comparison between our method and the previous work, we chose the same SOC benchmark, which is the common evaluation platform developed by MIT, as the common ground, and synthesize the RTL using the Synopsys 32 nanometer library. And we also chose the same sets of target nets, which is the encryption key nets in the AES module, the data bus nets from the processor to the AES, and the obfuscation key nets in the processor. And here I show the reroute attack effort results for 4 groups of implementations. The design with no shield nets, at all, and the previous work results, and the one with only shield nets, and the one with the shield plus other nets. And the design here in the table refers to which layers are all shield nets routed. And we can see that in general, the original design layout, the red one, causes the least reroute attack efforts and thus provides the worst protection. And the shield nets plus the other nets would achieve the best protection. And we can see that the M6 and M7 is the best design that can achieve the best protection. So, and for these 3 groups of target nets, we can see that the attack efforts for the data bus would require more, and the encryption key is the least. So before, we have considered that that the edits would so before we have considered the situation where the probing of each target net is independent of all others. However, in reality, attackers tend to possess only a limited number of fib probe tips, but there would be more than hundreds of target nets. Oh, sorry. And there tend to be more than hundreds of target nets. So the attackers may not be able to perform the probing all of the target nets at the same time because overlapping of the circuit edits would happen on the topmost layers. So here I show a simple example. You can see that the figure A and the figure B would be fine because there is no overlapping of the added vias But for the figure C and D, you can see that there is a overlapping on the top for the vias. Thus, sorry, I don't see why there is and the overlapping via just disappear. But the missing part is where the added vias should be. So we might need to we need to move the probing area to a different area to avoid the overlapping. And here shows the evaluation results of the reroute attack efforts in a dependent manner. So first, we have counted the number of the iterations implemented in order to make sure that there are no overlapping of the circuit at its location. And as the number of iterations increases, the attack efforts for all designs would also grow, because on one hand, if the overlapping happens, we need to identify a different probing area, which is time consuming. And second is that if different probing area is chosen, it is possible that it may not result in the optimal reroute attack efforts, and which will increase the, for example, maybe the added traces and the added vias. And we can see that in the results, we can see that most of them would require 1 or 2 iterations to find to make sure there is no overlapping, and about less than 10% would require more than 5 iterations. And we also perform the implementations on the shield plus other and the shield only. And you can see that M6 plus M7 and M6 plus M8 layer brings more cost than the M6 shield only. And sometimes nearly 50% increase can be observed in some case. And finally is the visualization results. I just showed the dependent manner and the differences between the dependent and independent. You can see that if for the probing area 1 and probing area 2 would overlapping as shown in the overlap point, and we might need to move the probing area 2 to slightly to the right to avoid the overlapping, and the results would be more. And the attack efforts would be more in a dependent manner. So finally is the conclusion. So to conclude our work, we propose a framework that can effectively evaluate the layout level reroute attack vulnerabilities. It is a linear programming-based approach that can identify the worst case scenarios of reroute attacks. And we found that 2-layer shield structures brings more attack efforts cost than a single one. And the orthogonal has better performance than the parallel. And in the future, we hope to do the more generic fib circuit edit attacks. And we hope to resolve the scalability enhancement issue. Yeah. Thank you.
So Islam Tawfiq, the Ohio State University. Great work, Minyan. Thank you for the presentation. So
Thank you.
I just have a question related to the results table.
Okay.
So if you look, yeah,
Here
yeah,
or-
exactly. So coming from the silicon perspective, you know, so
Yeah.
I'm just curious about the overhead that you added over here, because my understanding that when you apply the kind of rerouting, etc., you add more wiring and metal and all of that, right?
Yes.
So this is going to affect all of the performance of the design that you have, and probably violating some DRC rules and stuff like this. So how practically can you comment on how practically we can adopt the method and apply it? Sure, sure, okay. So with the result, I think you added like this is 135, the length in millimeter, and then 527 millimeter, right?
Yes.
So this is like extra wiring. You're using like 4 times the wires or something like this, right?
Mm-hmm. Yeah.
Okay. So these extra wires are going to add delays and all of that. So that will affect the performance of the design, right? So it adds security, but it has a cost.
So you are asking like how practical our results?
Yeah, I just need to understand, you know, how to adopt the technology.
How to adopt the?
Yeah, the technology that you're developing here practically to design
Yes.
something.
So you basically you want to ask like how to achieve the implementation, like how to add the shields or?
What is the cost of adding the shield, you know?
What is the overhead?
The overhead.
Oh, the
The
overhead.
overhead of your method.
Oh yes,
Exactly.
yeah. Yeah. Let me think. So yeah. So you're asking like what the overhead to implement the design?
Yeah, to implement the security countermeasure, like the countermeasure.
Okay, yeah, I see. I see what you mean. So yeah, I think so the design we have implemented we mentioned our overhead in another paper about the in the bypass, and I think you can see more in that check that paper in more detail. But and also we evaluated the overhead in terms of the area, power, and the routing.
Okay.
So I think the routing is the most overhead source, which would increase like more than 20%. And but for the other 3 overheads, they are all like less than 10% compared to the original design.
Oh, okay.
Yeah.
Okay.
Yeah, I think maybe you can check the. Sorry. I think bypass attack. Oh, sorry. Yeah, that's all right. Yeah, maybe I can share our paper.
Sure.
Yes, sorry.
Thank you.
Thank you.
Thank you. Let's thank the speaker again. And our third presentation is on dual-channel EM power attack using mutual information and its real-time implementation. The presentation is given by Yunkai. Yunkai is a PhD candidate from the Fins Lab at the University of Florida. He's thrilled to participate in HOST once again and share his experience, favorite search on dual-channel EM power attack using mutual information and its real-time implementation. The floor is yours, and let me open your slides. this is? It is below this.
So, hello, my name is Yunkai, a PhD candidate from Fins Lab, University of Florida. Today I'm glad to share with my recent work, dual channel EM power attack using mutual information and its real-time implementation. Okay, let's start. So nowadays, the IoT devices and CPS systems widely spread world. So from automatic car to smartphone, these devices deeply affect the ongoing 21st century. However, these devices have possibilities to leak secret information in the field. The transition of the voltage level inside the MOSFET of the encryption model in these devices could leak information inside channels when they encrypt the secret informations. And based on this principle, in the past 20 years, many related side channel attacks are proposed, and many encrypted modules like the AES or ISA are proved to be breakable. However, these traditional side channel attacks are not always being effective. So when they collect traces, they need to hear from traditional side channel systems like the oscilloscope and EM probe. So to our mind, they are too large. For some scenarios without enough space or without a stable cable, so these devices cannot be easily implemented. And also these devices have the oscilloscope such as oscilloscope EM probe, they are too expensive. So for the to us in this paper we use oscilloscope MDO 3000 series, and it costs over $16,000. So it's very hard to implement them out of the lab to monitor various targets. And also the traditional side channel systems lack ability of remote communication, remote processing, and remote data collections. So if we want to achieve some real-time implementation, it's very hard to let the traditional side channel system to implement them. So in this paper, we develop a mutual information-based feature selection methods to implement the SE attacks in real times. We first proposed a mathematical analysis to quantify the gains made by combining EM and power channels. We then successfully proposed methodology on real-time on a PCB board named the real-time dual channel platform. For short is RECP. So it's a coin-size PCB, which is showing here. You can see the comparison between the RECP and the coin, and its size is very small. You can insert it into a sneaky place inside the CPS. So the RDCP could collect the EM and power trace at the same time and do the real-time collecting, processing, and internal, and then transmit the data via Bluetooth remotely. We also perform experiment offline in real time for all 16 subkits of an AES 128 module and show improvements for measurements to disclosure compared to single channel EM and power. So to our mind, the traditional side channel power and EM attack could be classified into two groups. The first one is profiling attack, another group is non-profiling attack. So for the profiling attack, people collect thousands of traces and use these traces to generate a statistical model, which describes the variation of EM power, EM power at the times. And when testing traces come, so people could use the testing traces to compare to this statistical model so that they can use fewer traces to extract the secret information. And for the non-profiling attack, there's no need use of the statistical model. So in this paper, three attacks is mentioned: machine learning attack, differential attack, and correlation attack. The first machine learning attack belongs to the profiling attack. Last two belongs to the non-profiling attack. As we said before, these traditional side channel attacks, they lack ability of real-time implementation, and most of the work, they only rely on a single EM or power channel. So in our work, we rely on both power and EM channel. We select feature from two channels and to generate combined traces. The purpose of doing that is to make the combined trace contain more information than the single channel. So in our mind, if we could get more information in the trace, it could give us more chance to crack the information. So for the real-time dual channel attack, there are three issues very important: how to quantify the benefits of the combination. Second is how to select the features. Third is how to implement in real-time mode. For the first question, there are two related works we have found. The first one, they use concatenation method. which concatenate the power traces after the EM traces. They use the entropy method to describe the benefits of the combinations. Second one, they use the sum of the square of EM and power features and then add them together to over the standard deviation of these features. This method is more like an improvement of correlation tags. So both of two related works they wrote 10 years before, and there's no dimension reduction in their solutions. So if we want to implement the attacks in real time, dimension reduction is very important, because the biggest issue we met in the real time implementation is try to save the memory. So in our work, we use the mutual information method to select the best features and best combined coefficients, and then use RDCB to implement the two-side channel attack in real time. So here is the preliminary background. The X is data, means the features of combined trees. This class is we build class based on different sub-key values, and entropy is a measure of uncertainty of a variable, random variable. In this paper, we transform the entropy into its Gaussian distribution format for simple calculations. So in this case, we only need to deal with the standard deviation of the features. This also happened to the mutual information. We changed the general format to its Gaussian distribution format. So here's the overall workflow. First step we use is the feature collection. We load the template into target board and then collect EM traces at the same times. And then we calculate the standard deviations of these inputs, the training EM and power traces, and then put them into feature ranking functions to calculate the top index and coefficients. So in the last step, in the testing field, we combine the testing EM and the traces with the coefficients trained in the feature selection phase, and then shrink the size of the combined traces based on the index we select in the feature selection phase. In the end, we put them into attack algorithm to extract a key. So here shows how we do the linear coefficient optimizations. So the P stands for the power feature, EM stands for the EM feature. Z is the combined features. So we use linear alpha to combine these two features. So we first take approximations, Gaussian distribution approximations of mutual information I. So the purpose of doing the mutual information is we want to build a relationship between the coefficient alpha and the mutual information. We need to find the alpha which makes the largest mutual information. So that is why we need to take derivative of I to find the max I. So in this case, we need to so the derivative of f alpha has 3 items, f alpha. So since all the standard deviation is larger than 0, so first item is larger than 0. So, and the second item, since alpha is in the range of 0 and 1, so also a lot larger than 0, we only need to care about this v alpha, which is listed here. And in the end, we only need to find the 0 point of v alpha and plug into the f alpha, and compare the zero value of v alpha to find the best linear coefficient for the combination. And here shows how we do the linear combinations. So first is when input raw trace comes, we shrink the size of the input testing traces based on the coefficient we trained. So shrink the size and then normalize them into the same range. In the end, we use a coefficient to generate the combined trace. Here's a simple example. For example, the first feature of the power trace is 0.55 volts, and first feature for the EM is 0.37 volts. If the coefficient is 0.98 volt, we do it linearly and calculate the coefficient value for calculate the value for the first feature is 0.365 volt, and this also happens to other features. So there are 3 attack algorithms mentioned here: correlation attacks, differential attack, machine learning attacks. I think most of you are being familiar with these 3 attacks. So for the correlation attack, we take the index of hypothesis which owns the highest correlation value, and differential attack, we take the index of max difference between set 1 and 0 based on the hypothesis. So for machine learning attack, we generate a model of difference between difference of set 1 and 0 and target bit, and then when testing trace come, we use the trained model to calculate the outputs. So here shows how we implement the attack in real time. So first we want to say when implementing the attack algorithm in real time, the biggest issue is to save the memory. In RDCP we use PGA Spartan 3500 to do the processing and do the collecting. So it doesn't have too much memory. So, and in this case, we need to bypass the large memory save, and also bypass the hard calculation. And this all happened to the correlation algorithm. That is why we give up the correlation tag algorithm in real time. So in real time, we only implement the machine learning tag and differential tag. So for machine learning tag, we first train the classifier in the offline mode, and in real time mode, we can directly take their coefficient and its bias. So we turn the decimal calculation to the integer calculations. And in the differential tag, we process the trace one by one, and then turn the division calculation to multiplication calculations. And for the experiment setup, it has two modes. In the experiment section, it has two modes. The first mode is offline mode. We use oscilloscope and EM probe. Second mode is real-time mode. We only use RDCP. So a target we choose is Arduino Uno. So when we do experiment, we first do the profiling on Arduino Uno board 1 and do testing on Arduino Uno board 1 and 2. The offline experiment result is presented here. So as you can see, the combined channel, if you use less traces to achieve the 100% cracking result. So the combined channel is more efficient than the single EM and power channels. Also, as many other paper cited, the EM channel is better than the power channel. We also successfully implement the proposed attack against the different board, and 43% and 22% improvement versus single power and EM in differential attack, and 61% and 34% improvement versus single power and EM in machine learning attack. We also implement the related works, two related works, and the proposed attack is more efficient than the previous two work. So for the real-time experiment results, compared to the offline mode, the more traces are needed in real time versus the offline mode. The reason is for collecting traces in real-time mode, we use RDCP, and in offline we use oscilloscope. So the voltage range and the sensitivity of the oscilloscope is much better than RDCP. So that is why the traces collected by those oscilloscope is better than the RDCP, and more traces are. That is why more traces are needed in real time. And also in real time mode, power is better than EM. So this is not the same as in the offline mode. So this is because when we collect the EM traces by RDCP, the EM antenna, we split the EM antenna into 4 different layers inside the RDCP, and that deeply affect the SNR ratio of the EM traces collected by RDCP. So that is why power is better than EM in the real-time mode. So even though the combined channel is still better than the single channels, and 23% and 56% improvements versus power and EM in real-time differential attacks. So slightly more traces are needed in board 2 due to process variations between different boards. So for summary, this is the first implementation of real-time key extraction in situ, and it made it more efficient by combining EM and power channels. Maybe real-time could be new perspective for side channel attack communities. We will also share the EM power attack traces on Trust Hub. So for the future work, we will design new version of RDCP and upgrade our malware and Trojan detection from single channel to dual channels. Yes, we already wrote a journal paper about the malware detection, so we will upgrade it. And with the new version of RDCP, we also do the test framework on Mask AES and the RISC-V implementations. In the end, we want to say thank you to Army Research Office for the support of the whole programs, and thank you for you guys who come to watch my presentation. Thank you. Any questions?
Guilhèm from University of Cincinnati. So very nice presentation and interesting work. Just have one quick question. So let's say if you have a scenario, for example, if you do have very good quality of power traces, but on the other hand, you have relatively high, kind of like a poor quality of EM traces, for example, if you have a lot of noise from the EM channel. And then with that, if you do use both channels for the side channel attack, do you think that will actually affect the performance of the model, or it will actually make the machine learning model more robust? So yeah.
So in our work, we have two modes. In the training phase, we need to collect the EM traces as good as we can. So yes, as you said, maybe the EM traces is bad, but we will use the mutual information method to calculate the relationship between the traces, the channel itself, and the secret information. So if the SR ratio of the EM channel is affected, so the algorithm will let the combined traces select more from the better channel. For example, with power, we'll select more about the power. So coefficient is where make the whole combined traces more like the power channel. So if one channel is much better than another channel, so you can see the combined channel is more like the better one. Yeah.
Thank you.
Oh yeah, I just have a quick question. Like, you are combining power and EM side channels, but when we think about physically, they are essentially the same thing, caused by the time varying current from the device. So I'm just kind of, can you guys provide some insight in terms of how can you combine these two and generate new insight, new information that we wouldn't be able to do by power or EM alone? Yeah, thank you.
No. So we want to combine EM and power traces because we want to combine some traces for example from the EM that power traces is misses because in the same time point the EM maybe it has much higher variations than the power. So in our mind that will have more information than the power. And also, so in our method, we use mutual information to calculate this relationship to choose the best features. So in the related work, the first related work, you can check it mentioned. So at different time points, yes, they are from the generation of the EM power. They have the same reason, but at different time points, different channel they have they contain. Sometimes the EM contain more information. Sometimes the power contain more information.
Thank you.
Yeah.
Thank you. Let's ask the speaker again. Thanks for your attention. This concludes.